Okay, well, we'll just get started. So let's talk about the hypoxia paper. Who wants to go first with that? Start with you, Isaac, on the upper left-hand corner. What's going on there?
Kind of drawing a blank right now for most of it for some reason, but it was basically that the nitrogen from states along the Mississippi River and in the Mississippi River basin going into the Gulf was causing algae blooms, which were depleting the oxygen.
Okay. Yeah. Anybody else?
I didn't really understand what like carbon was contributing to.
Sorry, say that again.
In the beginning, it talks about how like nitrogen producing carbon contributes to the problem. I didn't really understand that.
Yeah, so there's this, we talk about the water cycle and there's the carbon cycle. Well, there's the nitrogen cycle too, right? So there are these microbes that live in the soil, and they're often associated with the roots of certain plants like legumes, and they fix nitrogen. So what fixing nitrogen means is that it takes the nitrogen that's in I guess it's a more oxidized form, and they reduce the nitrogen to a form that plants can utilize. And so the Haber process was a way. It's one of the reasons that rotating crops is good for the soil, is because you can put plants in that help reconstitute some of the nitrogen loss that is associated with other crops that you've grown before. So the Haber process was basically a way of artificially doing what these microbes do, and they can do it on a much, much larger scale. So there's several components, right, that they talk about that are sources of nitrogen to the Gulf. And part of it is that, there's nitrogen in the atmosphere, and part of it that it's happening naturally thanks to these microbes. I don't know, did that answer your question, Eliza?
I think so, yeah.
I have a question. So I know that Denmark is now a major exporter of produce because they do indoor farming. Mm-hmm. Would that be a way to avoid the buildup of salt in the soil?
Well, we're not really talking about salt and soils here. We're talking about nutrient loads.
Okay.
It's not really a question, but I mean, one of the main causes it was saying was fertilizer and like the runoff that was caused by that. And I don't remember what the exact like reasoning was, but I thought at some point in like a different article I had read in one of Emily's classes, they mentioned using like iron or something to help with the runoff to like bond to the nitrogen or something to make it less impactful.
Iron?
I thought it was iron, but it might have been something else. Like they wanted to essentially add something to the water for the nitrogen to either bond to or react with to lower the impact it had. And I don't really remember what that was, but I was hoping maybe you knew what it was.
I don't know what it is. But what are the classic strategies that, if you were in charge of like the Department of Natural Resources in the state of Iowa, for example, or at the federal level that you could encourage that would reduce the amount of nitrogen in the Mississippi?
You could probably manage just like runoff in general, like try to manage that from farmlands, or maybe regulate how much nitrogen they can use on their crops.
Okay, so right, so there are a couple of things there. One thing is that that satellite technology has allowed, and drones, quite frankly, as well, but a lot of satellites have allowed people to view their farms not just as one big farm, but as lots of little micro sections. And some areas have better soil and more water and more sunlight or whatever, so maybe they need less fertilizer. And on the other side of the hill, maybe the conditions are a little bit worse and they need more fertilizer. So instead of just spreading fertilizer on evenly everywhere, farmers are using this technology to know where to apply it, and they don't put it on places where they don't need it. Now, of course, there's an environmental consequence to that, right? If you put nitrogen fertilizer on and it's not needed, it's not being taken up by, at least by crops, and so it's more likely to run off. The other side, of course, is that it saves the farmers money. Fertilizer is really expensive, this ammonia stuff. So not using it when you don't have to is a good financial decision as well as an environmental one. Then you're talking about runoff as well, Gabe. What are the reasons why nitrogen is so likely to run off? Why does nitrogen run off rather than get taken up by plants?
I want to say that it bonds easily to water or oxygen, but I don't remember exactly what the reasoning was for why it didn't stay in the soil but the plants.
Well, it's water soluble, so you put it on, and if there's water around, if there's a lot of water, it's going to end up getting washed away, right? So the timing is part of it's just luck, not putting it on close to a few days in advance of a big storm. But the other part of it is that when you think about a farmer's field, I mean, we've all, whether you live in an agricultural state or not, you've all been in Iowa, so you know what those farm fields look like. And in the spring, right before the planting season, it's just bare dirt, right? And then when they're planting, it's these furrows, which are basically little stream channels. And the street, in the old days, like in the late 19th century and early 20th century, farmers weren't really thinking about soil loss and erosion. And so they would literally just go in straight lines across their fields, right? Up and over hills and whatever. And that's a disaster because you're basically creating little stream channels when you're going straight up a hill like this. You're basically creating all those little stream channels for the water to run down to become channelized. And as it starts running faster, it's going to erode. So it's too bad we can't do this field trip. There's a really cool place in northeastern Iowa that I normally take this class to. It's called Big Spring. It's a trout hatchery. So you get to feed the trout, and there's this really interesting guy who works there. There's a little dog running around. But it's right on a creek. And when you stand on the edge of the creek on the near side and you look across, right, it drops down into this little floodplain, and then there's the water, and then it comes up the other side, and you can see the bank really clearly. It's exposed. It's not all overgrown or anything. And what you see is from the bottom up about, I don't know, 1.5 feet is kind of gravelly, and it's the old regular floodplain. And then on top of that, there's literally like 3 or 4 feet, maybe 5 feet of just fine grained stuff. And you couldn't miss it. I mean, it couldn't be a more distinct transition from this kind of lower level granular stuff to this huge section of fine grained uniform material. And when geologists started looking all over the upper Midwest, Iowa, northern Missouri, Nebraska, Wisconsin, Illinois, you see this kind of thing all over the place. And you know what all that fine grained stuff is? Anybody want to take a guess? That fine grained stuff from the land surface of the floodplain down to the gravelly stuff?
Silt?
From where?
It's silt from the fields, because they were
Yeah.
doing the lines that you're talking about.
Yeah, it's topsoil. So the beautiful, rich, dark, we call them A horizons, but topsoil is what it would be. The topsoil was basically denuded by bad agricultural practices in decades. I mean, literally decades. Every time they'd go in, they'd break up the sod. And in the old days, you talk to, like, there was my next door neighbor is an 85-year-old ex-farmer. And so he was trained as a farmer, 70 years ago. And back in the day, he says, that they would have, if you were really kind of macho, good farmer, you'd get that plow down really deep and really turn up the topsoil, right? Well, you don't need to do that. There are all these new agricultural practices like no-till farming and other kinds of things, where they try to disrupt the soil as little as possible, because the more you disrupt it, the more susceptible it is to erosion, right? The other thing, of course, that happens is the more you turn over the soil, the more you bring up organic carbon, like old roots and bits of organic matter, to the surface, where they can oxidize and break down. So you're actually compacting the soil, you're losing components of the organic material. Anyway, so as these guys were going straight and creating furrows that went straight up and over hills, they were just losing topsoil like crazy. And it was, the Dust Bowl was largely a function not of a big drought. We have tree ring records that show us that the Dust Bowl drought was really a pretty minor drought. The reason it was such a problem was because of the agricultural practices that had preceded it. So anyway, that was a long couple of tangents, but to get back to the nitrogen conversation, if you can keep the water from running off the field, or if you can keep the water at least from running into streams, then you're able to trap the nitrogen on the farm field and keep it from getting into the rivers, where it can go to the Gulf and cause this hypoxia. And so one of the things that's done a lot, or that's encouraged a lot, are buffer strips. You guys have all seen this, right? When you're driving along, you'll see that if there's a hillside, there's kind of a little rivulet running up the middle of the hillside. Instead of plowing right through that rivulet, they'll leave it covered in grass all the time to keep it from eroding. And then on the edges of farmers' fields, particularly near waterways, they're encouraged to leave as long a buffer as possible of just grasses, so that when water is running off, carrying all that nitrogen, instead of zipping right into the nearest riverway or stream, it soaks through the grasses, is more likely to be infiltrated, and is more likely to be taken up by the vegetation there, which then keeps it out of the river. So anyway, there are all sorts of mechanisms that are being used. Try and put less on, use it more smartly, keep it from getting into the rivers in the first place. Okay, and then you noticed, I think, right, if you looked at the map carefully, here, I'll share my screen. And if you look at this, this is total inputs of nitrogen. Can you guys see this right here? You can see all the different rivers and stuff draining to the Mississippi, but this black shaded area in here is where the most nitrogen is being added. What does it say? 15,000 kilograms per square kilometer per year. So that's like, what is that? That's 35,000 pounds or something of nitrogen. And you can see that Iowa's like right here, right? So we're right in the hot spot of the places that add so much nitrogen. But then if you look at where the nitrogen is actually running off, despite the fact that all of these states are adding lots of nitrogen, a much smaller area is the one that's losing the nitrogen. And Iowa is losing the nitrogen like crazy. There's Iowa. So we're doing a really bad job compared to our neighbors like Minnesota or Nebraska or South Dakota, or whatever, of retaining nitrogen on the fields. In fact, I believe that, traditionally what people say is it's Indiana, Illinois, and Iowa are sort of the big three that are doing the most harm. This is a very old paper, though. This is, 20 years old, so things may have changed. Okay, we'll stop with that, and let's go into the next paper. What was the next paper?
Was that the Orange River one?
Sure, let's talk about the Orange River one. Who wants to start with that? Somebody who hasn't contributed yet.
So the paper talks about how you can do using blocks of limestone to oh wait, no, I don't think it talks about limestone, but it talks about like having plants to artificially precipitate out mine waste, or you could use bacteria and plants to do it passively and not having to spend money on a plant to do it.
Okay, so let's back up. So what's the problem that's being addressed here?
Mine waste, metals oxidizing in the tunnels dug into the mountain to get minerals, and then those oxidized minerals like aluminum, arsenic, and other heavy metals getting dissolved into the water that goes into the mountains, and then what comes out is a bunch of toxic water.
Okay, so what kind of, good, Joey, so somebody else, what kind of minerals are the problem?
Pyrite is a big problem because when it oxidizes and combines with water, it turns into acid. And
what is it that's in pyrite that's the problem?
Sulfur.
Sulfur. So there's a whole class of minerals called sulfides, which is a metal attached to sulfur. So what is it that's attached to sulfur that makes up pyrite?
I want to say lead, right? Yeah. And since the water becomes so acidic, it carries more metals, which become more soluble in acid. And then as a result, the water just like sweeps away a whole bunch of heavy metals that got into the local creek and whatnot.
Yeah, so it's iron sulfide is pyrite, but there's also other really common minerals, not quite as common, are lead sulfide and zinc sulfide. But they're just, so whenever you get sulfur around, it bonds with whatever metal is there. There's just a ton of iron in the crust. So there's a lot of pyrite around, and it reacts with water and oxygen and forms, you oxidize the sulfur, and when it reacts with water, that oxidized sulfur makes sulfuric acid. So what's special about metals, and what's the relationship between the solubility of metals and pH?
Are you asking me? Or?
No, I'll go on to somebody else. Thank you. Somebody who hasn't spoken, but yeah.
The lower the pH, the more metals can dissolve into the water.
Right, right. So the more acidic the water, the more the metals are mobilized. And so you have all this acidic water formed from the oxidation of pyrite, and as it runs across the rocks, it leaches out metals, right? And some of those metals are really dangerous. Most of the metal is the iron, because there's so much iron, but you can get other things like Laura or Joby or somebody was saying, right? Like aluminum, which is toxic to a lot of microorganisms, and cadmium and arsenic and other things like that. So how were they, Joby kind of mentioned this briefly, but how are they treating this mine waste?
They were mixing it in sodium hydroxide to increase its pH.
Yeah, so sodium hydroxide is a really strong base. And so when you mix something with a pH of whatever, 10 or 11, with something with a pH of 3, right, depending on the mixing ratio, it's going to move the pH up. And then what happens? What's the point of adding all that sodium hydroxide to the water?
To force the metals to precipitate out.
Right. And then they said they had to do one other kind of special thing to help get the precipitated metals out of solution. What was that?
Polymers.
Yeah, what are polymers?
Polymers are, sorry. It's a, how do I, God, I'm sorry, I'm blanking.
That's okay. They're just these little organic molecules
Yeah,
that
it's a molecule structure. Help.
and they're really good at absorbing um, other ions. So things like metals in solution, any kind of particulate will bond to the polymer. And why do you need to have these little tiny bits of metal or iron or whatever they are bond to the polymer? Why does the little bit of iron just sink out of solution anyway? What's the point of adding the polymer?
So the metal particles, it gives something that the metal particles can latch onto.
Yeah, but why do they have to have
Yeah.
anything to latch onto? Isn't metal, precipitated metal, denser than water? Didn't it sink anyway? Why go to the trouble of adding these polymers? Why not just add the sodium hydroxide and be done with it? Samantha, I'll ask you.
Is it because like the metals don't precipitate out into like larger clumps?
Why do they have to be larger?
Because if they're not larger, then we can't filter them out.
We're not filtering them out though, right? We just want them to sink to the bottom.
Is it because the water is moving?
And what does that do?
It washes them away.
Sort of.
The faster it's moving, it picks them up.
Yeah, right. So the idea is that you want them to settle out quickly to the bottom. And if they're these micro, tiny little particles, they're able to stay afloat. They're certainly denser than water, but when they're super, super small, they can actually get caught by little eddies in the water and kept in suspension. But if you add these polymers, the metal will clump into bigger pieces and it'll be so big it just sinks to the bottom. So then what do they do with all the metal that's settled to the bottom of the leach pond?
They compact
Yeah,
the metal.
somebody who hasn't spoken yet.
Uh-huh.
Going around the room here. Somebody who hasn't chimed in yet. Thanks, though.
It's a kind of sludge substance, and they compact it into like a cake-like substance, and they put it in the landfill.
Yeah, they just haul off to the landfill, but it's like hundreds of thousands of pounds a day or something, right? That they're doing it, and luckily that's only going to have to go on for another couple of years, right? And then the acid mine drainage will stop. Isn't that how it works?
I mean, how would you?
Joby, somebody who hasn't spoken yet. What do you think, Clayton?
Can you repeat it?
Luckily, they only have to add this polymer to the pond for a few more years, because then and haul it off to the landfill, because after that, the acid mine drainage is going to stop coming out of the mine, right? So why is that?
I'm not really sure.
Well, why would the acid mine drainage stop coming out of the mine?
Well, eventually it has to run out of like the material, doesn't it?
Does it?
Well, there's not like an unlimited supply of the material.
Well, how long is the tunnel?
I don't remember.
Willie, what do you think? They're going to run out of acid mine drainage in a couple of years?
I don't really know
Yes,
either. I don't know how to answer that question.
Huh?
I don't know either.
Well, what do you need to make acid mine drainage? What are the 2 or 3 things you need?
The like minerals along the tunnels.
What
And
kind of?
then water
You need water.
and
What-
oxygen. Where does the water come from?
Yeah.
Precipitation.
Okay. So is it going to stop raining?
No,
Okay. Are we going to run out of oxygen?
no,
Are we going to run out of minerals inside the mountain?
probably not.
Probably not. So acid mine drainage is going to stop in a couple of years. True or false?
False.
False. It's a perpetual problem. Once you set this system up, until you do something to permanently like seal off, backfill the entire tunnel with cement, which would be unbelievably expensive, or you just treat this stuff forever, because this is a perpetual problem. And obviously, in some cases, it's very localized. You got one big tunnel with lots of water coming out, and you can sort of have it in one particular sort of point source. Or you can have, as they talk about, just dozens and dozens and dozens of small streams draining out, all of them orange and polluted and dead, in which case it's much more expensive because you have to set up these remediation plants all along the way. So it's a real problem. Do you think that would be something we'd have to worry about in Iowa if we had, let's say we had gold mining here? Let's say that somebody was digging into the rocks underneath Mount Vernon 100 years ago and created all these mine shafts and had pulled out all the gold. And now we've got these, water soaking in, running through. Would we have to worry about acid mine drainage?
No.
Why
Because Iowa's, we have mostly limestone, and limestone neutralizes the acid.
Right.
And so
That's it.
Yeah.
That's it. So acid mine drainage is a huge problem in places where there's no limestone. It's the same with acid rain. When I was in junior high, the cover of Time magazine showed these dead lakes in the Northeast, the Adirondack Lakes. When I was in college, I went on this pre-college canoe trip, and the lakes were dead. These beautiful, beautiful lake after lake after lake, they were dead. There was moss in them and maybe some little minnows, but all the life was pretty much gone. And it was because of acid rain. And acid rain formed because coal-fired power plants would burn all this coal that had all this sulfur in it. And the sulfur-rich fumes would go up into the air and it would mix with the water and form sulfuric acid. And when it rained in New England or wherever, the rain that came down was really, really acidic, like 3, 4 pH. And if it happens to fall on top of Iowa, it runs through the limestone, it gets neutralized instantly, no big deal. But if it falls in Vermont or the upstate New York, it hits rocks that are like granite, slate, you know, and there's nothing there to neutralize it. So that acidic water runs into the lakes and streams and, you know, leaching aluminum and stuff out along the way, which causes all sorts of problems. So one of the great environmental wins of the last 30 or 40 years has been making acid rain in the United States just a non-entity. It's a nothing anymore because the Environmental Protection Agency required coal plants to take the sulfur out of the coal or out of the smoke. So it's a little bit different with acid mine drainage, right? Because it's just all over. It's in little bits all over rather than having a few coal-fired power plants. But most of the gold mines on Earth are in things like granites, and you're not getting any buffering. You're not getting any neutralization of the acidity if water runs over a granite. All right, let's talk about the last paper, which was the Bangladesh arsenic paper.
So they've started pumping groundwater for agriculture.
Wait. Where's Bangladesh, Crystal?
Asia.
Okay, let's zoom in a little more.
Okay. South Asia.
Okay.
Okay.
Yeah,
So they've started to pump.
Wait,
What?
I don't know where
What?
Bangladesh is.
Do you want a map? I don't.
I want you to, yeah, I want everybody to know where it is. What does it border? Is it like near, is it near Vietnam?
No.
Is it near
No.
Pakistan?
No, India. It's between India and Myanmar.
Okay, so it's the east of India, right on the ocean.
Yeah.
Okay, sorry.
Yeah.
Take
Yeah.
it.
So it's South Asia, but like near Southeast Asia.
Right, coastal, low-lying, flat, Southern Asia. Okay, go ahead. Sorry to interrupt.
Okay. So.
Crystal, don't let me interrupt you. Go ahead.
Okay. So they've started pumping groundwater for irrigation instead of just for wells as a way to like solve like drought related famines. So they're like, oh, this is great. We can have groundwater and make sure our crops stay irrigated. But this like drawing the like more water out than just their drinking water from the ground has like lowered the water table. So when they get monsoon rains, so again, this is South Asia, in between Southeast Asia and South Asia. So they get monsoons.
What's a monsoon?
So when there's really intense monsoon rainfall and they've lowered the water table, it like makes the exchange of water from the rain into the ground really high. So it's like circulated, which draws a lot of like waste, like sewage into the ground. And it's thought that the sewage, like the carbon from the sewage changes the groundwater chemistry, which like makes arsenic come out from the sediments in the ground. And then that makes their drinking water, which they're also getting from the same place, more like have more arsenic in it, which makes it not really safe to drink anymore. So they have to dig lower for drinking water because they're using up like they're yeah. Sorry, I don't know how to explain that.
Yeah, no, that's good. Right. So this is an old paper, and there are lots of models and theories about exactly what's causing the arsenic problem. But the solution appears to be that they need to stop drinking or irrigating, even because the arsenic can build up in the soil and in the plants from shallow wells. They need to start using deeper wells, which is a an easy solution, although it's much more expensive, right, to drill a deeper well.
Yeah.
But it solved the problem. So in the last paper, the Orange River Run Sewer paper, we were saying that there's a problem with metals like arsenic or iron being mobilized because of pH.
Mhm.
That when the water is more acidic, the metals are more mobile in
Mhm.
water, right?
Yeah.
Is that what they're talking about here? Are they talking about changes in acidity? Well, you know what, Crystal, you did a good job. I'm going to call on somebody else now.
Cool.
Maya.
Yeah, so I don't believe they were talking about changes in acidity. They were talking about how like the circulation of water in the underground aquifers from like the water that was taken out for irrigation is replaced by the monsoon water, and that carries with it like I think organic chemicals or compounds that could trigger like release of arsenic, and so that was the problem because this is the same aquifers that people are using for their drinking water.
But what's happening to release the arsenic or to mobilize the arsenic?
I am not 100% sure what chemicals are being brought into the aquifer by monsoons.
Okay, Chloe?
There's the arsenic is bonded to iron, and then there's like the nitrate or whatever that they're using to irrigate, right? That's taking, I don't know I can't remember if it said nitrate, but some other mineral that's then like releasing the iron from the arsenic and bonding with it, so then it's releasing the arsenic.
Okay. Someone else just saying something? Yeah, so it's a little bit more of a complicated situation, right? But we often diagram, like think of this as an XY graph, right? And you have pH on this axis, and you have redox on this axis. So we understand what pH is. That's pretty easy, right? Whether something's acidic or alkaline. The EH, the redox or the EH axis is a little bit more complicated. But basically, you can think of it like in the natural world, a lot of it is just how much oxygen is around. And so if you have acidic waters, metals are generally more mobile than alkaline or high pH waters. And if you've got reducing conditions, meaning not a lot of oxygen around, metals are generally more mobile than if they're oxidized. And once metals become oxidized, they're more likely to precipitate out of solution. So the acid mine drainage was largely a function of pH changes, and the arsenic well problem in Bangladesh seems to be more of an EH or oxygenation sort of phenomenon, where the raising and the lowering of the water table is causing differential amounts of oxidation and reduction of these minerals that the arsenic is in. I think we talked about, did we talk about in the whole subsidence discussion about how maybe we didn't talk about this, how organic rich soils like bogs, when you dewater them for farming, they collapse on themselves, they subside. Did we talk about that at all? I can't remember if we did or not. Subsidence is you remember what subsidence is all about, right? You pump the water out and you reduce the fluid pressure so the effective stress goes up and the aquifer kind of collapses and the land subsides. Well, subsidence is also a big problem in organic soils. So like northern Minnesota, if you've ever driven around in northern Minnesota up near the Boundary Waters, there are all these like bogs and the road goes through the bogs and stuff. And if they were to come in and dig a trench and kind of dewater, allow canals to let the water out, the organic rich sediments that have been waterlogged, the water table falls. And now this part is, instead of being soaked in water year round, it's now got air that's can circulate through it. So the air gets in and it oxidizes the organic matter, and the oxidized organic matter breaks down and turns into carbon dioxide and goes away. And so the soil compacts as it gets dewatered. Well, what we're seeing here is kind of an analogous to that. You're dewatering, at least for part of the year, you're dewatering the aquifer so that air, or in some cases, organic carbon and stuff from the surface can get down, and that changes the chemistry. And then, so the water rises in the next monsoon season, which are the really intense rains in like June, July, August. And then they pump the water down in the dry season, and then the water level goes back up the next. So you're constantly sort of changing the redox conditions of the sediment, and oxidizing to free up the arsenic, and then flooding it, and the reducing conditions return, and the arsenic can be moved back into the well. Anyway, it's a complicated scenario, but it's like a, I don't know. I think reading this paper in conjunction with the Orange River paper is neat, depressing, but interesting, because you've got one problem being caused by pH and the other being caused by EH. And yet the result is basically the same. You're mobilizing these dangerous metals. Okay, let's move on. Were there any questions related to the hydrogeology of regions thing that I put on the videos this morning? It's really hydrogeology from 30,000 feet, but the main part of it is to know that two things, really. There's water everywhere. You just have to dig for it. The question, though, is whether or not the water is going to be any good. And in some cases, if you keep digging deeper and deeper and deeper, the water gets saltier and saltier, and eventually becomes, for most agricultural and consumption purposes, it's no good anymore. That there are different kinds of aquifers, and that the kind of aquifer is largely controlled by regional geology. So in the Pacific Northwest, you have all those volcanic deposits. In Florida, you've got all these low-lying limestones. In the upper Midwest, you've got sandstones and limestones and so forth. And they're all kind of independently acting as different types of aquifers and reservoirs. So I encourage you to go through the document that spells all that out in more detail. Look for your home state on there, or your home region, and make sure you get a sense for where your water's coming from, because it's good to know that stuff. It's in your backyard. And what else? What else? I guess that's about it. It's now 2:45 Central Time, so in about 9.5 hours, your Cadillac Desert paper is due in my inbox. I'll get comments back to you, generic comments about whether I think you're on the right track or not by the end of the weekend. And that's it. Okay. All right. Well, have a good weekend, and I look forward to seeing your papers tonight.
Wait, Ron.
Yeah.
So we have to do another, like a final draft on Monday, right? So we'll edit over the weekend and then turn it in again. Is that?
Let's see. When does it due?
I think it said Monday.
Yeah. Yeah, I'll make that, because I'll get you your papers back, your comments back by Saturday afternoon.
Okay.
So you'll have more than 24 hours to incorporate them. My comments will be light, but basically I just want to make sure that you're on the right track. And if you are, then there won't be much to say.
Okay, cool.
Okay. See ya.